I'm sure people will wander in. I hope you can hear me all right. We don't have a microphone. I'm in the strange position here of having a light blinding me, and all I can see is some vague faces from time to time if I move out of the light. If any of you have a question, please just shout up, because I won't see any hands. So, having said that, could I just have a quick hands up for anyone who doesn't know what RISC OSM, the app software for RISC OS is, because then I can, if there are any people who don't know anything about it, I will give a slightly longer introduction. Right, I don't see any hands, so I won't explain that in immense detail, especially as it's taken, it has grown and grown and grown in capabilities over the last 11 years, so there's quite a lot to say about it if I was going to do a full demo of all of that. Anyhow, today we're releasing a new version of RISC OSM and new versions of email and A2B and Nomine and one sort of bits of software. Most of those are free upgrades, but RISC OSM and email there's a small charge. We've been doing quite a lot of work on improving Unicode support. Now, I realise this is kind of not desperately interesting to UK users because, on the whole, we don't tend to use any accented characters, let alone anything even more exotic like Cyrillic or Greek. But it's been quite a bit of development to do, and RISC OSM obviously has to cater for countries all over the world where different scripts are used. So just to give you a flavour of what we've done, if I go to the new map window in RISC OSM and select Poland, we can start typing the name of the Polish city, Łódź, which you will probably be almost unable to see from the projector. There it is in its with its Polish accents properly. The L with the slash across, which makes a worse sound. There's an O acute, which is available in Latin 1, so that's never been a problem. And then the Z has an acute accent as well, which isn't a character available in the Latin 1 alphabet that most of us use. So for a long time we have supported these characters in the gazetteer and in RISC OSM displaying them on the maps as well. But this latest release, we are also supporting typing these characters into any of the data entry fields in RISC OSM. So starting with the gazetteer here. So you'll see there, I hope, that those accents have actually transferred into the writable icon, and we can delete them again or type some more letters. So you're not losing that information when you pick from the gazetteer, it's got the correct characters in there. I just want to give you a little bit of a rundown about why this was quite a challenging development and what it all means, and indeed how it works. So I've got some slides which we'll just quickly go through. So way back in the day we had ASCII, the American Standard Code for Information Interchange. And the important thing about that is it was for information interchange. It wasn't necessarily designed for storage. You know, you could store things however you wanted. But for communicating between different computers, this was a standard code. And it's based around a 7-bit alphabet character set. Now, obviously in computing we always start counting at 0, so you have the bits there, 0, 1, 2, 3, 4, 5, 6, and then bit 7 wasn't used in ASCII. Well, it was. It was used for parity. So you could count the number of bits that were set in the rest of the byte, and then indicate with a 1 or a 0 whether there was an odd or an even number that was set. And that meant you could transmit 8 bits, which included an error correction mechanism so that you will be able to tell whether any of those bits have been switched during transmission. Of course, if 2 bits have been flipped, it didn't help because you wouldn't be able to detect that. So that's why we were limited to just 128 characters. And of course, the top row, the control characters shown with the black there, they were all for doing often very mechanical things with your teletype machine, like shifting the paper up one line, pushing your print head back to the start of the carriage, indicating the end of transmission or the start or end of a record of data. So all of those control characters were used for special things, and the character 127, which of course is 7 bits all set, was used for blanking. And the reason that was used was because on old punch cards, to wipe out a byte, you needed to punch it all out. If you've got some of the bits punched, punch it all out and then it'll be completely wiped and you can ignore it. So that's a kind of ignore character. So then, of course, we had to move on, and if you want to support accented characters, if you're not American and you have to deal with a few accents, as we indeed do in English with words like cafe, then you need some more characters. So the first step was, well, we've worked out better ways of doing the data transmission. We don't need that parity bit anymore. Let's use that, and then we can double the number of characters. In fact, we can even increase it beyond that because, well, to start with, you double the number of characters, but they also included a row from 128 up to 159, which mirrored the control characters, and so that row was not actually used in ISO Latin 1. But of course, various different operating system manufacturers started filling them in with other characters. So Acon Latin 1 has a few extra characters in here. It's got the OE ligatures, which are needed for French, which were missed out of ISO Latin 1, despite the fact it was meant to cover Western European languages. It's got various directional quote symbols. It's got these characters here, which are useful for Welsh. And it's got a couple of typographic ligatures for the FI and the FL. So that's Acon's standard. Of course, Microsoft puts things in different places. You'll also find directional quotes, but they're in different positions. So we were using all 8 bytes. And if you wanted characters that weren't Western European, there's other character sets beyond that. So you have ISO Latin 2, which is Eastern European. So you've got the C hat check there, which is used in Czech. You've got the L that I mentioned earlier on with the line across hanging in here somewhere, can't spot it now, and various others. And again, Acon filled them in with some extras in that 5th row down there. Then you get Latin 8, that's meant to support Celtic languages. It's got all the things that you need for Welsh, with the Y circumflex and so on, and others which are used presumably in Gaelic and Breton and so on. I don't know where all of these are deployed. And you can also have the ISO Greek alphabet. You'll notice that the ISO Latin 2, which is 88592, ISO Latin 8, however, is 885914, so the numbering gets very complicated and it's very fiddly to deal with. ISO Greek, you can switch your character set over to ISO Greek, but this just shows you also that it does depend on your font, so it's rather full down at the bottom. All you're getting in the Greek range is that mu symbol, which happens to be in the Honiton font because mu is part of ISO Latin 1, because you need it for SI units like micrometers or micrograms or whatever. So that mu prefix was put in there. So that's the only Greek character in Honiton. Obviously, you can only easily use one alphabet at a time on your computer, and so if you're wanting to go beyond that, you need Unicode. And here is yeah, this is not a display of Unicode. This is a display just of 8-bit characters again because it's illustration. But the way Unicode worked is, first of all, they decided, well, let's just have 2 bytes. UCS2 will have 2 bytes, that should be enough. 65,000 characters, plenty for everything you could possibly imagine. Except it wasn't. Sorry, and then they realised that, you've got big endian and little endian. Do you have the low byte or the high byte first? So that's a bit of a mess. And then they realised you need more than 65,000 characters, because although you can fit the whole of Chinese and Korean and Japanese and all the Roman and Cyrillic and Greek and Devanagari and all that kind of stuff into 2 bytes, once you start wanting to support Egyptian hieroglyphs and cuneiform, Babylonian cuneiform, and all sorts of writing systems that are no longer used, you need to go beyond those 2 bytes, and that's why we now have UCS4, which became UTF-32. So you've got 4 bytes. Now the problem with this is you have to rewrite all your software to cope with 4 bytes or 2 bytes per character, and that's quite a lot of effort. And also it's taking up a lot more storage. So this is where UTF-8 came along. So UTF-8 is a very clever encoding, which means that characters are stored in between 1 and 4 bytes, depending on where they are in the Unicode sequence. So a 1 byte Unicode character looks like this. It starts with a 0 in the top bit, and then you have bits from 0 up to 6 here available. And it's actually, this is the clever bit, it's actually exactly the same as ASCII. So these are all your ASCII characters. So you can take a text file encoded in ASCII, 7-bit character set. It's identical to the same characters encoded in UTF-8. You can just drop it in and you don't have to do any conversion. Once you move on beyond character 128, then to start with you will need this representation, this 2-byte representation. And the pattern that works for the rest of this is you see the number of 1s at the start, at the top end of the very first byte. That indicates how many bytes in total there will be. And then all of the succeeding bytes, the continuation bytes, they all start 1, 0. It's very clever because it means that you can drop into the middle of a string. If you found you've hit a continuation byte, you can back up until you find one of these ones which has more than 1 at the start, and then you know that you're at the start of a character. Or you can skip over to move to the next character. It's very easy. You don't have to read right from the very start of the file to work out where the character boundaries are. So it's a very neat encoding. So the way this would work is, supposing we're looking to encode the graph here from the isolatin one. So that's character 160 plus 32, 196. That's character 196. No, it isn't. It's 160 plus 16. Anyway, it's somewhere around there. Suppose we're encoding 196. What you do is you fill in the bytes, the bits from this end. So that's the least significant bit. And you'd be needing 1, 2, 3, 4, 5, 6, and then 7, 8. So the isolatin 1 characters, you'll find they all fit into 2-byte representations, and all those 3 bits there will be 0, and then the rest of it will be represented in those 2 parts of the frame. So that's basically how it works, and you get higher and higher numbers up to the full 21 bits that is supported in Unicode. They don't go all the way to 32. 21 bits is enough, we are told, and hopefully they won't have to change that. So, how has RISC OS support developed? Well, when we implemented RISC OS, we started using this RISC OS Unicode font library, Ruffle. And this does the important business of what's called glyph substitution. So you remember the problem of the Greek font there, which Homerton only has a mu. So if you've chosen to present your map in Homerton, but there's no other Greek characters there, how do you get the rest of them? That's where Ruffle comes in. So Ruffle when an application that uses Ruffle starts up, it will have a look at your font directory. If there are any new fonts there that it hasn't seen before, it will scan those quickly, or slowly if you've got lots of them, to find what all the characters are in your fonts. And then you can use the Ruffle library to paint your characters onto the screen or put them into your draw file, like RISC OS does. And any which don't appear in the font you selected, it will find a suitable alternative font which has that character in, and it'll switch to that font and put the character up on the screen or into your draw file. And this was produced by the NetSurf developers. It's a big part of NetSurf. That's why NetSurf can display web pages from a wider range of languages than Latin 1. And the NetSurf developers also implemented a module called Icon, which allows you to convert from one character coding to another, and the TTF2F application, which allows you to convert a true type font into RISC OS format. So all of those tools together were built by the NetSurf folk. John Mark Bell, in particular, did a lot of this work, and it's really set us up well with the basis of what you need for supporting a wide range of scripts. So you'll see at the bottom, this is just an example, the SWIs, the software interrupts that we use in RISC OS, font paint, font string width, font scan string, all of those different things which are used to put characters on the screen or to work out how wide a string will be when represented in a font. They all have equivalents in the Ruffle C library, which you can compile into your program. And you just make those changes and do the calls slightly differently, and it does all the hard work. Now, the other aspect, of course, so that's the rendering, and we've been doing the rendering for 5 or 6 years pretty well now. But how do you get the stuff typed in? You've got the WIMP key pressed event. So all of the characters that you type on your computer will go through the WIMP key pressed event, and that tells the WIMP application what key has just been pressed. And the brilliant thing is, look, it's a word. The character code is a word. So they didn't limit it just to a byte. We've got 4 bytes to play with, which is absolutely perfect for Unicode. Absolutely amazing. It's really, really helpful. Apart from the fact that Acorn decided to put in the range from 256 up to 511 special key codes for print, F1 to F9, tab, end, left, right, up, down, page up, page down, this, that, and the other. Which means that we can't use the key pressed event with a full Unicode range, because those are precisely the Unicode points, character points, which are used for Eastern European scripts and all sorts of stuff. So it's really unfortunate. If Acorn had chosen some really, really high numbers, we'd have been fine, because they could have been out of the Unicode range. But this was all being done before Unicode had been thought of, so you can't really blame them for that. So we have to cope with all the... So what actually then happens behind the scenes, if you are typing in a Unicode with a Unicode alphabet on your RISC OS machine, and suppose you type an eacute. Eacute in UTF-8 is 2 bytes. So the WIMP in fact sends you 2 key pressed events, one straight after another. First one is the initial byte of the UTF-8 encoding, and the second key pressed event will be the second byte. So you're still getting an 8-bit stream of code, of character codes, and you then have to reassemble them into an actual Unicode character point if you are typing in Unicode, which all makes it rather a hassle, but still quite good fun to develop. So what we're going to see now, that was those slides. How do you actually do the typing? So I was just demonstrating earlier opening a new map, and I typed in Lodge just by typing LODZ, yeah? And RISC OS is good at removing the accents from anything that's been indexed and matching things up, so that's perfectly fine. But if you're wanting to search in Greece, for example, OpenStreetMap will not necessarily have transliterations of all the Greek place names in Greece, so you may need to type in some Greek. So to do that, there are various different applications, and this is where we get a few of them up. First of all, you've got the CHARS system here. So I'm going to just quickly choose a slightly more exciting font. If we change CHARS to Greek, or to, sorry, this is a bad example, so we don't want Trinity. Let me find a font which has lots of characters. So, free serif. So, if I change that to Greek, you'll see that there's lots of Greek characters there. And if we change it to UTF-8, you will see we get some Greek characters further down. Sorry, there's different categories, we can get the Greek ones up like that. But you'll see that they are grayed out. And that's because CHARS is aware that our RISC OS machine is running with the alphabet set to Latin 1. So whereas if you are looking at it in Latin 1, they are black, and when you click over any of these characters, it will send it into the keyboard stream. When they're grayed out, it doesn't do that. So we can't type the Unicode characters using CHARS because it's clever enough that it knows that we haven't got our alphabet set to UTF-8. If we want to set the alphabet to UTF-8, it's quite simple. We just open the task window and say UTF-8, alphabet UTF-8, and we should then find that now you see I haven't tested this. It still grays them out, and that's because I think you have to reselect the font. That's right. So you reselect the font, and then it works out that you've actually changed your alphabet. So we can now type those characters in. I'm going to go for the Greek ones again. So let's get in a kappa and a lambda. Now you'll see this little window at the bottom. Zap is saying, warning, character is not available in target encoding. So we would need to change the encoding of our text file to match, otherwise it doesn't make sense. Anyway, this is all a bit of a headache. There are other options as well. There is key map, and there's more keys. More keys is rather nice. It doesn't put up an icon on the icon bar, so I can't tell it's running. But with more keys, you can press Control Out and then the letter you want, and then put up a little window at the bottom where you can pick the letter. You can use the arrow keys like with your phone or whatever, or you can just jab and type it like that. Again, Zap is going to object because it doesn't like the character. So let's go back to RISC OS's new map window, and we'll show you that. Oh, yes, and then this thing here down here is key map from Paul Spranger's, and it's got a virtual keyboard like that. So you may remember back on this the talk, sorry, the slides, which was called Plain Talk. Let's not get confused. Unicode has this quite exact structure. The UTF-8 has a very exact structure. You have to have precisely the right number of characters, continuation characters, following the ones that introduce the multi-byte sequences. And this means that it's actually very, very reliable. You can pass a string to a program, and that program can work out whether it's an 8-bit encoding or whether it's UTF-8 very easily, because there's so much structure in the UTF-8. Any slight variation from that, you'll be able to tell, oh, it's not UTF-8, it must be an 8-bit encoding. So to get a character, a Unicode character appearing by accident in a UTF-8 encoded sequence, well, you'd have to have a character from the bottom, for a 2-byte sequence, you'd have to have a character from the bottom row, followed immediately by a character from this row. And it's hardly likely that you're going to have that in a normal document. So what this means is, inside RISC OSM and in email as well, we're able to ignore the alphabet setting. We don't have to have alphabet set to UTF-8. We can just have it left on Latin 1. Whoops, sorry, I can't type because Greek keyboard's on. I knew that was going to happen at least once during the demo. So we can go back to Latin 1, and Paul Spanger's key map is perfectly happy to send the Greek codes through, even though we're in Latin 1. It will send 2 or 3 bytes for each of these. If we click in there, what will be happening behind the scenes when I press that alpha is that there will be 2 or 3 bytes sent through. RISC OS gathers them together, spots that they look like a Unicode code point, and makes an alpha appear. So I can type in alpha, theta, eta, nu, yes indeed. You see, I'm going for Athens because it's about the only place in Greece I can reliably spell. So there is Athena, and we can then go and draw the map. So that's how it works in RISC OS. And what's more, in your pins and tracks, where you might have pins that you're wanting to describe, we can edit the descriptions, and in all these descriptions you can have a whole load of Greek characters as well now, which you didn't used to be able to do. So all sorts of parts of the software have been updated to support the full range of characters. I have to say, by the way, that Hebrew and Arabic are not supported because Ruffle doesn't support right-to-left character scripts, unfortunately. So, we then have, we're going to show you quickly, you also get some advantages with JPEGs. So, for example, in a JPEG, you might have a caption. Here is one from a holiday, which I'm dropping on RISC OS. And if we look at the caption there, you'll see it says Shundra Palestautis Yemen. Now, I don't know whether there is a standard for the encoding of text within JPEGs, but we have found that variations on RISC OS puts the characters in Latin 1, and we have found other examples which are in UTF-8, which have come from other computers. So RISC OS is capable of working out whether it's a UTF-8 or a non-UTF-8 string, and then converting it appropriately for display. So that just makes it a lot more reliable. When we were displaying this before, it loaded into Impact OK, because that was assuming Latin 1, but in RISC OS it had a couple of characters instead of, and the O allowed it expanded into a couple of characters which were totally unreadable. So all of that's been improved. And I'd just like to show you IMP Email. So IMP Email is our mail merging software which can work with databases like Impact and Powerbase, but it also can work with CSV files. So here is an example of a template for getting a subscription renewal from a number of subscribers. We drop on the CSV file. Sorry, I'll just open the CSV file and zap. And you'll see it's got a lot of very peculiar looking characters because those are the multi-byte sequences. So Zap hasn't identified that. And we will drop this onto here, and you'll see that the CSV file is loaded up nice and clearly with some Greek text, some Polish, and some Cyrillic. And if we test one of these, so here's a beta. Sorry, I'm going to just run printers because it's going to complain if I don't. Printers, choose that. So IMP Email can mail merge your emails via these fields. It can also mail merge attached documents. So here we have an Innovation Pro document, and it's got merge commands in as well. So let's see what happens. If we click test, It pushes it through, and we see Dear Elizbieta Kaminska with all the correct accents, and there's the place name and so on. Now, Ovation Pro doesn't support the full Unicode experience. So what has been pushed through to Ovation Pro in email will convert those characters to the nearest Latin 1 equivalent it can find. And so you get Elizbieta Kaminska without any accents. You see there's no acute on the Josefa bit, and the rest of it has been de-accented. So it does the best it can. If you move on to someone like Volodymyr Zelensky in Kiev and test with that, you'll find that, unfortunately, what comes through to Ovation Pro is a load of question marks because it can't cope with the Cyrillic, and there isn't a transliteration table built into the icon module. So that's the limitation. But you'll see that you get perfect stuff here in the email, and that will go out on, through email gateways and arrive at your destination successfully with all those characters intact. So, I think I've probably about run out of time very nearly. I was going to show you some other things, but they were things that I've shown you before in the RISC OS North show. The only other little demo is this plane spotter, which, if I've got the right map up on here, which I haven't, let's just go to we go to Heathrow Airport, which I can't do because I'm typing in the wrong script again. This doesn't seem to be working. I think I've bitten this out this bit. But anyway, suffice to say, we released some Python demos a year and a half ago about how to use APIs on the web with Python and to integrate them with RISC OS. This one called Plane Spot, which we haven't released yet, was knocked up in about 45 minutes yesterday morning because I got it on my list of things that I wanted to try for the show. Ran out of time, but it only took 45 minutes to get something that does actually put current locations of aeroplanes onto the map. So I'd encourage you to have a think about APIs that you might want to look into, and we will try and make some of this easier to do by giving you some example software you can tweak and alter and benefit from some of this stuff. So let's stop there. There may not be any time for questions now because we must be on to the next person, I think, but get them in at the stand over there. Sorry for overrunning.